differential equations lesson involving slope fields and Euler's method, and in particular, here in Objective 2, being able to use Euler's method to approximate solutions of differential equations. Differential equations in general are kind of tough to solve. How can we approximate what the solution could be? And Euler's method gives us a way to find the solution to any desired level of accuracy. We just have to take smaller and smaller steps. The picture that's in the background here is the idea of course correction. If you take a look at this orange path here, this is a flight path of an airplane, and then right here it switches paths to course corrects to this yellow one here. This picture here was taken from one of the images that were published when those Malaysian planes went missing a few years ago, and they were trying to figure out where those planes might have gone by plotting some different flight paths for them. Okay, so in the previous couple of videos, we talked about the fact that what we want to do here is not necessarily solve the differential equations. We're trying to visualize what they look like, and that's what a slope field is going to help us do, or approximate their solutions, and that's what this objective is all about, using Euler's method. So again, this is sort of like some sort of course correction. And if you look at the image here, we're launching some sort of satellite from Earth that's at 8:12:05 towards Mars, and Mars is this brown dot that's right over here. And you can imagine how tough it would be to launch something from this planet and trying to get it to another planet further in the solar system. And it may involve some sort of course corrections. And you can see they course corrected a couple of times here. So the first path was the blue one. Yeah, we're far off, so we need to course correct. And now it's on this dark green path, and they had to course correct again. And then there's a smaller one right in here where they finally got it onto Mars. Okay? All right. So let's say that we're in this slope field generated by, I need the slope field right there. Y prime is equal to x plus y, and it has the initial condition 0, 1. And let's go ahead and put in this is the actual solution curve. But it's not one that I know. I haven't been able to solve this yet. What we're trying to do is approximate a solution to it. So this grayed out image here is just giving us a base of what our answer is supposed to look like if we could actually get it. All right, at that initial condition, 0, 1, if I plug that into the differential equation, 0 plus 1 is 1, it should have a slope of 1 at that point, and it goes through 0, 1. So maybe we can use the equation y equals x plus 1 at that point to approximate the curve. It's not perfect, but it's dead on at that point, and it has the slope at that particular point. And the further that we move to the right, the less and less accurate our answer is going to be. So we're going to have to fix that, right? So let's say that we use this line, this tangent line here, to approximate the solution at x equals 1. So if I plug 1 into that equation, you can see visually here it hits at 2. So we're going to say that at x equals 1, the solution to our differential equation is about 2. And we can see here that obviously we're off by a little bit. And if we were to use this line, this blue line, to approximate anything further to the right, it's going to be less and less accurate. So, what we're going to do then is we're going to step at this particular point, and we're going to course correct. We're going to change our direction according to the slope at that particular point. So now this has the point 1, 2. If I plug that into our differential equation, 1 plus 2 gives me 3. The slope at that new point should be 3. So I'm going to course correct through that point, and here's my new equation like this. It's getting a little bit better. It's at least mimicking the shape of that actual solution curve. All right, so now we're going to use this new graph to approximate the solution to the curve at 2. So at 2, I follow it up to the line, and it looks like it hits at about 5. And again, it's off by a little bit. And the more that I use this particular line, then the more and more inaccurate my answer is going to be. So maybe I course correct at that particular point too. This is 2 comma 5, I plug that into the differential equation. It should have a slope of 7 at that particular point. So it looks like this. And you can continue to make these kind of course corrections at each one of your little points. And you can get as accurate as you want to. The question here is, how could you improve this approximation? What could you do with the same exact technique to make it even more accurate? Well, how far to the right did we step? We stepped just 1 unit. If we had stepped, say, a half a unit, this would be even more accurate. If I stepped a quarter of a unit, it'd be even more accurate. You can get as accurate as you want to. It just makes the math a little bit more tedious, and you have to do it a little bit more. All right, the amount that we step to the right is called the step size, and we usually use the letter h for it. It's the same thing as a delta x. It's what your x's are changing by. And we could have decreased our step size to get a more accurate picture right here. So here's our step size of 1 for our h. And on the AP exam, it's sometimes something like a half. It could be a quarter. It could be 1. So here are some different plots using Euler's method and various step sizes. So here is the step size of half that we just looked at. Step size of 3/4. No, it was 1/4. No, the other one was 1. That's what it was. It was 1, 3/4, a half, and a quarter, and you can see that we're getting closer and closer to what that actual equation is supposed to be, depending on our step size. Okay, so this is where we're going to pause this video, and in the next one we're going to get into the details of actually how to use this Euler's method to approximate a solution.